Hello everyone, welcome back. Let's continue with the air bearings. And as we understand that air bearings are important part of any precision systems. So we talked about different kind of stages, different kind of air bearings. And what we understand that air bearings with the orifices, they are very fundamental and basic. And if we understand the working principles and how the different mechanical characteristics depend on these different parameters of an orifice type air bearing, actually that will explain a lot of things, and it will also facilitate new designs and new design of group patterns, new design of air bearings which can be embedded in the systems to achieve higher precisions. So we'll first go through this orifice type air bearing, and majority of the work is from my research while working in Singapore at ASTAR in SIMTech, which is Singapore Institute of Manufacturing Technology. There I worked for more than 5 years as a research engineer and work on various precision systems for semiconductor industry for applications in precision systems. And we also work on developing different kind of air bearings, and that was also part of my master's work there. So but it's very fundamental and basic to any kind of air bearings and air bearing stages. So we'll cover it and go through that one by one. So as I mentioned earlier, and it's clear from here also. So different geometries we can see. It can be circular, it can be rectangular, it can be even journal bearings, and then there can be orifices, and so you can see orifices here. There can be pockets, and there can be groups also. So there are different combinations, and it can be embedded on the bearing surface itself. And in all of these are aerostatic bearings. So pressurized air is fed through, and then it passes through the orifices and then passes through the bearing surface, and that's how it works. So that is the general construction structure. So just consider this circular case. So maybe consider this part with the circular pocket. So only the half section is shown, and so what is important to understand in this kind of bearing is, one is the flow through the orifices. So it's the supply pressure is fed, and of course it has to be clean and dry. So it should be supplied, and first it passes through this orifice. So that is one kind of restrictor, and then it flows through the bearing surface. So the basically we are looking at these two fluid flows. So is supplied through this, and then it is just discharged to the atmosphere. So we try to look at it, and from the fluid dynamics point of view, the fluid flow. So first consider the flow through the orifice, and so there are a lot of assumptions, and one should be aware of these assumptions, whether it is valid. And whenever there is a deviation, we should look back and look at those assumptions. So first is the flow through the orifice. So what is shown here, and what is assumed that there is no pressure losses upstream of the throat, and the pressure downstream the jet, the pressure is the static pressure in the throat. Second is the flow through the orifice. That's the first part. That's how it flows. And second is the flow through the bearing surface. So first it is, this is the flow. So we are talking about this area only. And the second is the flow through the bearing surface. So here also what we assume, that is the flow is laminar and the pressure is constant over any section which is normal to the direction of flow, and there is no slip at the boundaries. So these are the basic assumptions, and we still consider laminar flow, and then we do the analysis. So accordingly, we will also try to derive and find. So yeah, means if it's required, we can always refer to the literature. So no need to remember all these complicated formulas. So we can always refer if we want to understand, but for the time being, just to have an understanding how it works and how we can calculate a different parameters, I think we can just use this formula. So if you just consider this flow through the orifices and just assuming it as a jet flow, then the mass flow rate can be written in terms of the area of the cross section of the orifice, and okay, different pressures what we are assuming, the supply pressure and the downstream, the pressure in the pocket. So but in the orifice, uh, we assume that the pressure is constant and there is no pressure difference. So and consider that we can calculate the mass flow rate here. Of course, the CD is also equally important, coefficient of discharge. So that was for this section. So flow through the orifice and as a jet. The second is the mass flow rate through the bearing surface. So when it's already here, and then how is flowing through the bearing surface. So it's again a flat surface we are talking about. The diameter is, and it's a circular geometry. So we can take a section and then we can, assuming it's a laminar flow, we can calculate the mass flow rate for a given air gap, and then okay, so H is the air gap we are talking about, and again PD is the pressure here in the pocket, PD, and outside is atmospheric pressure, and so then we can calculate, and B and A are these geometric parameters what we have. So these are two mass flow rates, and we can always try to solve for a given mm, air gap, and we can accordingly find the pressure distribution here. So what would be the pressure distribution? And once we integrate P over area, so P times dA, so we can take a annular region and integrate over the from A to B. So what we see here, and in the pocket, this region, the pressure is constant, which is PD. So that's why it's PA square by PD. So that is the area times pressure, and then for the annular part we integrate. So pressure distribution, we know if this is the pressure distribution, then we integrate, so A to B, and then we can find the overall load capacity, which is given in terms of PD and PA, and then B and A, so geometric parameters of the bearing. And once we differentiate, we can also find the stiffness. So what is the, so when the extra load is applied, what is the change in your gap, and that can give us the stiffness value. So it's a non-linear systems, so it's not a linear characteristic. So and we can always use, so for instance, I use MATLAB and mm, then also solve it and try to find. So different, what is the load capacity for a given parameter for a given geometry of the air bearing or air bearing pad, and what would be the stiffness given the pressure supply pressure of the air. So once it's a set and we have the mathematical model, the good thing is we can vary different parameters and we can see the effect of those parameters on particularly in this case what we are looking at is the, this is the load we are talking about, and this is the stiffness. So basically these are the two characteristics we are looking at, and we look at different parameters. So for instance, if you change the orifice diameter, what is the effect? And along this is H, which is the air gap. So we solved it in MATLAB. We can write a small code. So these days can be written very easily using Python or any software. So basically solving those equations, mass flow rates, and trying to find what is the, because it has to be same. So we can find the air gap, and then we can also calculate the load capacity and the, so once we have the pressure distribution, we can calculate the load capacity, and then we differentiate with respect to H and we can get the stiffness. So that's how we plotted it. And here we change the orifice diameter. So from here, what you can see, the D is changing from zero 0.1 to 1 millimeter, and then we see what is the effect. So one thing what we observe that the total load capacity is same irrespective of the orifice size, and is, I think as we load the air bearing, and it doesn't matter how big or small is the orifice, as we start putting the load, the air gap will get reduced, and so that the pressure distributions, it will be more or less very similar, and that's why I think the total load capacity may not change. So and that's why what we see that it's all converging to the same point, and we can always check. So if we consider a constant which is equal to the supply pressure and is like more or less distributed all along the surface, what would be the load capacity? So from there also we can find it. So it's not a parameter, so it doesn't change with the orifice size, the total capacity. What we also realize that for larger orifice diameter, and which is evident from this, so we can just consider any of the plot, and if we choose one diameter, particular diameter, the change in air gap with load is large when the orifice diameter is large. So for 1 millimeter, we can see a very big variation, but for a smaller diameter, smaller orifices, the change in air gap is really small. And because of that, what we see is the stiffness. The stiffness is very high. So as you see, as the orifice diameter decreases, the maximum value of stiffness increases. So actually these two plots are related, and that's why when, so like if we look at this statement and this, actually they qualify and they support each other. So if the diameter is small, the orifice diameter is small, the stiffness is high, and that's why means one has to understand that the stiffness, uh, the total load capacity is not function of orifice, but the stiffness is definitely a function of the orifice, because it's a provided the restriction, and whenever there is a change in load, it's there might be some backflow or one two, and that will be getting restricted by the restrictor. So it can be the orifice itself, or we can also assume a kind of area which is like allowing the flow on the bearing surface. So that is also acting as a restrictor, and that's the reason that when there is a load, it's also getting reduced. The air gap is getting reduced. So, and we can also understand that what is the order of stiffness. So you can see it's very high. So 10 to the power 7 Newton per meter. So one can imagine that what is the stiffness of this air bearings, but correspondingly, if you look at the air gaps, that's also very small, of the order of tens of micron. So it's really, we are really working at a very small air gap, but at that at that range, or at that air gap, the stiffness can be way higher than any kind of contact type of bearings. So whether it's a journal bearings, or whether it's a rolling element bearings, it can be comparable, or even the air bearings can be stiffer. So uh, means people may feel that okay, it's air, so how come the stiffness can be so high? But once you understand the fluid dynamics, what you realize that yes, it's getting trapped, and although the flow is there, but if you want to have any change, it may not be possible. So or there is a very small change in the air gap. So I think it's very important to understand this part, how air bearing works, and once we know, we'll be confident to apply these elements in our design. But we also know that the air gap is for the maximum value of stiffness is very small. So similarly, what happens if we change the supply pressure of the air? And again, it's a load here, and this is stiffness we are talking about. So load capacity versus stiffness, and now we are changing the supply pressure. So maybe here the orifice diameter is fixed, and then only changing the supply pressure, and we see, and it's quite evident that the total load capacity increases with the supply pressure, because the ultimate pressure what we have is higher. So that's why we can see that there is an increase. So similarly, the air gap, there is no much variation in load capacity for larger air gaps. So if you see here, this region, uh, that change is not there, not that much. For the stiffness, what we see that the maximum value of stiffness again is increasing with the supply pressure. So that upward trend is there as we increase the supply pressure. But what we also notice that the peak value of the stiffness is nearly at the same air gap, and we can correlate with the size of the restrictor. So because if it's a function of the restriction, the air gap on the one side, the other side is the orifice diameter. So the restrictions are provided by these two restrictors, and it's a geometric parameter. So of course then the stiffness or the location, so the air gap more or less is the same. Of course the stiffness is changing, it's a function of supply pressure, but where it happens, that's more or less fixed. Again, the increase in stiffness is prominent near the peak value. So you can see the encircled part, the, the the change is prominent there. So the optimum air gap is defined, and accordingly, the for the given diameter, but we see that the change in the stiffness is a prominent there. Similarly, we can also see the effect of bearing diameter. So if we increase the size of the bearing pad, what will happen? And again, this is the load and this is the stiffness. Again, since the bearing diameter has increased, so of course it has a larger load capacity. So that is quite obvious, but we also see from here. So variation in load capacity is prominent in all air gaps. So you can see it's quite distributed. So at every air gap is changing as we change the bearing diameter. For stiffness, what we see again, the maximum value of stiffness is increasing with the bearing diameter. But the peak value here again is nearly at the same location. So air gap is very close where the peak stiffness is happening. But we also need to understand that, like in case of supply pressure, is it possible to increase it further? So there are other kind of problems, and it's mainly related to fluid dynamics. And as we increase the pressure, all these kind of elements or the bearings, they are prone to instability, and usually it's called pneumatic hammer, and this is mainly because of the squeeze film damping effect. So it just get reverse and then it gets into unstable region, and then there will be a humming noise and it vibrates very vigorously, so at a very high frequency. But maybe the frequency is low, but then it makes a lot of noise, humming noise, and from that we can easily figure out that okay, this is something not desirable, and we should avoid that. So uh, when we are talking about pneumatic hammer or this pneumatic instability, what are the two things we might be looking at or interested is the supply pressure and the volume of air which is trapped inside. So that's why that is the reason we cannot have very big pockets inside in the on the bearing surface. So there is always a limit, and one need to understand that, and this is also a very active area of research when we try to solve and try to address these issues in air bearings. So, and particularly when you are working with the orifice type of air bearings, it's important to know what kind of instability we can have and how to avoid that. So based on this understanding and what is the effect of different geometric parameters or the input parameters on load capacity and the stiffness values of the bearings, we also come up with the design methodology, design approach. And if we are interested in designing these elements and or even to select, how to based on the requirement, how to choose certain parameters. So just based on this basic understanding, we try to come up with some methodology. And for instance, suppose this is our requirement. So what is the load capacity? What is the payload? What we expect? So payload, and it can be loaded when it's moving, the dynamic load and everything. So if we know that number roughly, so if we can always calculate. So let's assume it's of the order of 250 Newton, and the stiffness what we are looking at is of the order of 20 Newton per micron, or is in SI unit 20 10 into 10 to power 6 Newton per meter. So you can see that the stiffness value is very high, and of course the air gap, it also depends on what are the mm, manufacturing limitation, what kind of surfaces we can get. So let's not stretch ourselves too much and try to be to be within a limit. And suppose, let's say, maybe air gap of the order of 10 micron can be maybe better. So yeah, we say okay, 10 micron. So if we have this thing with us, then how to start? So of course, first we try to fix the supply pressure. So we may want to work with the supply pressure, what is available on the shop floor or what is convenient to work. So usually I think these are the numbers. So 5 bar, 6 bar, this kind of presses we are comfortable working with. So let's choose that supply pressure P naught. And if we have that supply pressure for that given supply pressure, so what we can check from here is a 250 Newton. If we put, so it's a total load versus air gap, and if we plot for different bearing diameters, so 30 to 80, and if we just put that 2050 Newton line, but we realize that okay, yeah, 2040 may not work because the load capacity for the given pressure may not be enough. So we have to go for bigger diameter. So yeah, 50 onwards. So let's go for the 60 millimeter bearing diameter. So from here we can choose 50, 60, 70, 80 also, right? So yeah, at least this is my boundary. So it has to be above this line. And okay, air gap is also we can have in our mind. If not, okay, again we can look for different supply pressure and we can negotiate. If suppose the bearing diameter is either too big or too small, then what is the supply pressure we can comfortably choose. So of course design is an iterative process, so we always have to be aware of that. So now looking at the stiffness plot for this, for suppose 60 millimeter if you take, and if you take this uh, supply pressure, and again we plot for different orifice diameter, what we realize now, we're talking about this stiffness values. So from here we realize that again the orifice diameter of 0.46 or even 8 may not work, because this is not acceptable. We want to have a stiffness more than 20 Newton per micron. So we have to go for this. So it means we have to go for orifice diameter of 0.2 millimeter. So I think while working with these kind of systems, one has to really fine tune and understand these values and these numbers. So it's not about millimeter or like centimeter, but many times it's in point 0.1, 0.2 millimeters, air gap of the order of micron. And I think one should always remember that, or remind himself or herself that what is the number one should always find. So orifice diameter 0.2, and if we do that, what we realize that this is the air gap 12 to 18 micron. That is the air gap we are talking about. So of course air gap also we mentioned that okay, it should be more than 10 micron, and here comfortably we are getting between 12 to 18 micron, so which is good. Moving on, once we check for these given parameters, so supply pressure, bearing diameter, and the orifice diameter, and if we look at the total load capacity, where air gap, and what we realize that that the air gap is optimum air gap is from 12 to 18 micron, and okay, if it's not suitable, we can always iterate, and if not, then we can also change the supply pressure. But we also need to understand that for air bearings to work, they have to be preloaded. Preloading is one of the key parameter, and air bearings works only if there is a preloading. And it's also clear from here that the kind of characteristic we are looking at, and the load changes from 180 to 330 newtons. So the preloading, and of course that includes the loading also in the positive direction. So the the air bearing has to be pressed. So if it's beyond that, the characteristic, so if it increases, of course the it can go till for in this case is not reaching 400 but lower than that. But if it's lower, then the air gap will increase the stiffness and those parameters. But what we also understand that is it has a mechanical intelligence, what we call it. So if we increase the load, the air inside on the bearing surface, it will get pressed and the air gap will get reduced. So there will be again the pressure over the bearing surface area will change so that it can take the load. On the other hand, if the weight is less, the preloading is less, more air will flow and there will be larger air gap. So it adjusts. So it's a self-adjusting, which is good. So we also need to do a lot of CFD simulations, and now we have a very powerful tools. We can always do that. So we can come up with the different kind of configurations, and we can always do simulation to substantiate what we have already observed. So in this case, there are two configuration we are talking about. So the first one is the circular one. So it's a quarter model, and at the center is how the air is supplied, and with the supply pressure we have, there is a pocket, circular pocket, and then it's a flowing through the bearing surface. In the second case, there is a annular groove all along, and then with the supply pressure, the air is fed, and then it goes to this annular groove, and then of course it flows out also from here. It is fed through, and then it radially flows out. So yeah, the dimensions here, micron and millimeter, and we did map meshing and compressibility, turbulence, those can be allowed. So here we have more flexibility. In analytical models, we always try to be conservative. We assume laminar flows and then try to find closed solutions. But when we are working with the CFD packages, we have more freedom, and with time there are means what kind of turbulence, what kind of other flows that can happen. We can always define our models in that way, and we can get the results and compare how is it deviating. Of course, it has to be also compared with the experimental results. But the good thing is, even before we start making these air bearings or air pads, this can be well designed using CAD, and then we can use these CFD packages to do the analysis. So we did that, and from here also is the supply pressure. If you see the pressure distribution, and it's quite evident that from the circular pocket to outside how the pressure is varying. For annular, I think the inside is more or less, and then it's flowing outside. Yeah. So we can see a very nice pattern, and so kind of particle flow also we can do and can simulate. So this also shows that how the flow happens inside the bearing, and of course it can also animate. So you can see that how it comes here and then flows in the different direction. Similarly here is, so it's quite intuitive, and we can also extend to full model also. So here we solved only the quarter model. So we also try to compare the CFD results with the analytical results, and what we see is a very good correlation in the pressure distribution. And of course, so there are certain assumptions. So we try to do that, and for different CD values, we can see they are more or less converging, and the dotted line is from the CFD calculations. So that is one part, like getting a mathematical model and then do the parametric study and understand how the air bearing works, and also use CFD packages to understand and get a sort of validation. But the real validation is through experiments only, that we have to always remind ourselves and understand. So what we also try to do is develop a setup, test setup, and whether we can, for a given bearing diameter and the different parameters what we have, can we do some measurements and can we characterize. So we develop a setup, test setup, so a test bench we call it. So here we have the air bearing and it's a press, so we simply apply the dead load here, and we can measure what is the air gap. So through the guide shaft is and on the sides, just to support here, we have air bushing so that there is no friction there acting. So the entire load is on the bearing itself. So here is you can see the enlarged view. So a specimen bearing is this. So you can see the air is, and there is a small orifice you can see. So it's just going through this. So in terms of dimension, you can see that these are all macro dimension, big dimensions. And the air gap, what we are talking about, is of the order of micron, 10 micron. So that's why many times it's not visible. But yes, one can see, and when you're doing the experiment, actually you can see. So up to 3 or 4 microns, you can see through. You can see the air gap. But if it goes below, very difficult to see and see things with the naked eye. Here again, there are some elements of precision. You can see how the bearings are pressed, how it's loaded. So some concept here. You have the load cell. So whatever is the load, we can measure and then see. So it's a very simple setup, but yeah, one need to understand what goes into this, and not necessarily it has to be complicated. So as a fresh engineer, we always uh, try to build things which looks very nice after rendering, but when it comes to functionality and when it comes to precision, what we realize that many of the features may not be required, and one should get away with those things as soon as possible. So if we can use simple features, simple blocks, it's always easy, always better, and it can save a lot of money to the company or to the any person who is working on these kind of setups. So it's not after one iteration, but many iteration happened before I was able to get rid of those complex and fancy things. So one should also remember that you need a air filtration system. So the air which is fed to air bearings, it has to be prepared. It should be filtered, and it should be dry and oil free. So there are pneumatics involved. So very simple, but we still need to have it. And I think we also understand that what is the size of the particles if it gets into the flow, and it can easily clog those orifices, because the number now we are talking about is zero point 0.2, zero point 0.8 kind of millimeter of that size. The air gaps of the order of maybe 4 to 10 microns. So it can always scratch the surface. So we work with this. So air bushing, and you can see the this blue line. So it's for the supply, air supply, and the specimen bearing is there. So of course, for measurement, we have these measuring probes, and we placed it opposite to each other, so that if there is any tilting, that can be averaged out, can be measured. So once we started measuring, and we put the load versus air gap, and we did it many times. So but we find that there are two plots and it's changing, and that's basically because of the tilting. Some tilting can happen and it stays. And if you closely look at the setup, what you realize that for tilting, the contact is a spherical surface, ball kind of thing on a cone sitting. So it's a physical contact. So it means there will be always some residual moment, and after that it cannot correct. And therefore, what we see here is evident, because it's moving from one side to other side, and there is a jump. But once we take the average, we can get a very good line, because the tilting effect, because it's 180 degrees, so that can be nullified. So there is an increase, but there will be equivalent decrease. And we also change it, and then so if we look at the average value, we can see that there is a clear trend. It shows a behavior, and load versus air gap. So very nice. So we did it, and then we also tried to superimpose with the analytical results. So, and then we also try to find the a stiffness plot. Yes, a stiffness plot may not be easy, so we have to do some kind of curve fitting, and then we have to take the differentiation, and then we can plot it. In some region, we see a deviation, and so those deviations are there, and I think mm, they are only happening at a very smaller scale, and so a small change in values, a small change in the or some assumption may go wrong at those scales. In our case, what we realize that the specimen what we have, we although we assume that is a flat, but once after careful measurement, what we realize that the bearing is actually not flat, but it has some kind of convexity, and so it's a concave. So of course, if the it's a order of micron only, but then it's not apparent with the naked eyes, but with the careful measurement, that's what we realize. Our analysis is completely based on the flat surfaces. So yes, means that's something we have to accept, and also means with the analysis. But for the majority of the part, it gives a very good result. And of course, we can always do some back calculation, and develop analytical model for a different kind of bearings, and always check this experimental results with respect to that. So we compare the different parameters again superimposed. So as I mentioned, these are like part of my work while working in Singapore in A star. So it's reported and one of the technical report, and it's easily available on internet. Uh, other thing what we also understand that of course the manufacturing part is not an easy task, and yes, there are limitations. So getting a flatter surface may not be easy. Getting a for even for the bearing pads that has to be diamond turned. So we have to really get a clean surface and the flat surface. So sometimes it's like aluminum, and it can be a mirror finish. So those things we have to be aware of. How to control the dimensions, the diameter of the orifices, that we need to understand. Yes, we have the theoretical basis. We can always mm, find that what are the some rough numbers we have to work with, and uh, but many times it's available for simple geometries. But if we have complex geometries, so suppose rectangular blocks or rectangular pad with the annular grooves, the theoretical basis might not be there, and we may have to resort to different kind of numerical methods or CFD tools for the studies. So again, we have to establish adequate mathematical or analytical models or simulations tools. And at the end, we definitely need to have a very good testing facility so that we can always claim. And once we are using these air bearings for developing systems for high-end applications, for precision applications, it has to be characterized, it has to be tested. So of course we need a very good testing facilities if you want to develop these kind of systems. So definitely there is other class which is porous air bearings, and that's there are a lot of work going on in that end, and the access to any kind of testing facilities can always provide us good insight, and we can always develop porous air pads for our own applications. So these are the results. Uh, there are some more examples, and this example is from MIT, from Professor Slocum's lab. And what he has done is he developed linear motion carriers. And as I said, that preloading is one of the aspect, one of the key feature which is required if we want to work with the air bearings. And in this design, what he has done is he has used this inclined linear motor. So what it does is it provides the traction, but at the same time it also provides the magnetic preload, which will be, so this preloading is in this direction. So what you can see, these air bearings, all air bearings can be preloaded at the same time just using that linear motor. So very nice design, and it can be used designed linearly. It can be used in a rotary table form. So here all the forces are mentioned, and if you are using it for machine tool application, then what are the forces, how you balance these forces. So again, here you see that he has used rectangular pads, and these are the preloads talking about, and traction, and these are the tooling forces. So how it will get balanced. So again, one can refer to this paper and can understand more about this design. So yes, he got it fabricated, and then how the assembly process, because these are very precision systems, and the alignment, those requirements are of the order of few microns. So what are the various steps when it has to be fixed, or suppose if you are using epoxies to embed things on the structure itself, like uh, what are the various steps. So each and every step is mentioned there, and so you can see that first air pads, and then okay, you put the epoxy and then let it cure so that the orientation of the pads are properly placed. And then okay, of course, the displacement and the weight loading we can see. So again, you can do all these measurements and try to validate, and can get the frequency plots. And at the end, one can always put the motors and test it for performance. So I think in today's class we talked about orifice type of air bearings, and try to find and try to understand how different input parameters affects the performance of a air bearing, particularly with respect to loading, load capacity, and stiffnesses, and understand through those plots, and then what is the design methodology if we want to select certain parameters. So we can always do that. We also try to understand through CFD simulations, like what are the how close is to the analytical model, and we can find a very good correlation. We also talk about the setup which is required, and if one is interested in working with their bearings and develop research facilities in their own place or in the company, these are little things might be required. So I hope this gives you enough confidence to start working with the air bearings, and of course it's a very nice area, and can once we start working can give us a lot of confidence. We'll cover and talk about more designs, and of course that's I learned, and while working with the different companies and different research institute, we work on these kind of air bearing systems. So I'll be talking about those things in details, so that one should be confident enough to take these problems in future, or most likely after this course you have the confidence that okay, we can do it and work on this kind of system. We can build our own designs, we can build our own systems for any kind of measurement, precision measurement, or any precision application. So let's continue. I'll stop here. Thank you.